Hello everyone. Today we're going to continue to learn chapter 1. In this chapter, we're going to learn the curvilinear coordinates, which include the spherical coordinates and cylindrical coordinates. Now let's start the class. Um, okay. First, let's see the spherical coordinates. Um, Here we have, let's say, a vector r or a position p. So if you connect the position p and the origin, you can get this vector r. So, um, so this position or point p could be expressed by the Cartesian coordinates by x, y, and z. So here we see the x, y, z axis, but sometimes it's more convenient if we use spherical coordinates. In spherical coordinates, we don't use x, y, z anymore. Instead, we use r, theta, phi. So in this picture, we can see r, theta, phi. So first, r, it's the displacement from the origin to the position p. That's the r. And then for theta, it's the angle between the vector r and the z-axis. And then the projection of this r on xy plane will be in dashed line shown here. And this dashed line form an angle with x-axis. This is the angle phi. So by defining the r, theta, and phi, you can define the position or a vector in the 3D space. So any points like P could be labeled by X, Y, Z coordinates, and it can also be labeled or expressed by the r, theta, phi coordinates. So this is the spherical coordinates. And now let's see. So r is the distance from the origin to the position, or the magnitude of the position vector r. And theta, which is the angle down from the z-axis, is called the polar angle. And of course, the range of theta could be from 0 to pi or 180 degrees, because if theta is 0, that means the vector is going up, which is parallel to z direction. If it's pi, means it's 180 degrees, means the vector is going down. It's in the negative z direction. So for phi, the angle phi is the angle around from the z-axis in, let's say, anti-clockwise direction. So let's say if phi is 0, that means it's in x direction. And then the range of phi could be from 0 to 2 pi. If it's 2 pi, that means it's getting back to x direction. Otherwise, it's some other directions in xy plane. And this angle phi is called the azimuthal angle. So the relation to Cartesian coordinates can be read from this figure. So now let's see how to derive the relation between xyz and r theta phi. So first, let's say x in, let's say for this position P, if we want to express the x in the r theta phi, or spherical coordinates, how to translate it. So first we have this r, which is the distance from origin to the position, or magnitude of this vector r. And then the projection of r on the xy plane is in the dashed line, which is shown here. And this could be written by, let's say, because this is 90 degrees, then this red dashed line is r times sine theta, because here that's theta means here this is also theta. So this line is r sine theta, and then if we look at the triangle in, let's say let me use another color. If we look at this triangle in blue, then in this blue triangle, you will see, actually it's not blue. Okay, now I'm selecting the blue color. If we look at the blue triangle, we'll figure out that actually here it's 90 degrees. So this part, this length is the x. It equals to the red line times, this is phi times cosine phi, which means r sine theta times cosine phi, which is shown here. X equals to r times sine theta times cosine phi. And then in similar way, y equals to r sine theta sine phi, because this is x and this is y. So, and for z, it's relatively easy. It's just this length in the blue dashed line. It's r times cosine theta. So that's the expression of xyz in the spherical coordinates. Okay, that's just some trigonometry. So if you're familiar with triangles, cosine, sine, then there's no problem for you to derive the xyz in spherical coordinates. So one thing we need to notice is that so in this spherical coordinates, you still have three vectors. So in Cartesian coordinates, you have three vectors, which are three unit vectors, which are x hat, y hat, z hat, and they are perpendicular to each other. Or we call it orthogonal. But here in polar or spherical coordinates, you still have three vectors, which are shown here, which is r hat, theta hat, phi hat. And these three vectors, they are also perpendicular to each other, or they're in the orthogonal system. And any vector A can be expressed in terms of them in the usual way. For example, if we have a vector, let's say this is from O to P, we define it's a vector A, then the vector A equals to the magnitude of this vector, which is AR, times the unit vector in R direction, and A theta in theta direction plus a phi in phi direction. And AR, A theta, A phi are the radial, polar, azimuthal components of A. In terms of the Cartesian unit vector, R could be written in this form, and theta is here, and phi is here. Again, if you want to describe R, theta, phi unit vectors by using these X, Y, Z unit vectors, you need to draw some pictures and do some trigonometry. So finally, you will get those equations. So you can do something similar to this. So here, we just gave the conclusion. You can remember these conclusions, or you can, when you need to use it, you can just refer to the textbook. Because in homework or in the, let's say, exams, you're allowed to use some equations in the textbook. If you need those equations, you can write it down in a cheat sheet so that in the future, you can easily refer to those equations. And of course, you're encouraged to try to derive the expressions of R theta phi unit vectors by using X, Y, Z vectors. If you have time, you can do it. Okay, now let's see the infinitesimal displacement in those three directions in spherical coordinates. So, so we will have three directions in, so any infinitesimal displacement could be decomposed into three components, which is the um, radial direction component, which is dr, and the components or direction in theta, and another direction is in phi. So let's see how to express an infinitesimal displacement in r, theta, and phi direction. So first, let's see the infinitesimal displacement in the r direction. This is very simple. It's just the dr, because if we look at the figure A, if the r has a very small change, then the change is just the dr. It's just an infinitesimal element of length in the r direction. It's similar to an infinitesimal element of length in the x direction. So if it's r, it's just a dr in r direction. Now, on the other hand, a little bit more complicated situation is the infinitesimal element of length in the theta direction. Okay, now let's see. If you have infinitesimal displacement in theta direction, which is shown here, then in trigonometry, the angle is almost 90 degrees if the d theta is small enough, or r, or the if the d theta is small enough, then this displacement is small enough, then this angle is almost 90 degrees. So you can use this displacement equals to r times sine theta, d sine theta. And it also equals to r times d theta, because if this is very small, then d sine theta and d theta, they're the same. So r times d theta, that's the infinitesimal displacement in this direction, in the theta direction. Or we can write it in d L theta equals to r d theta. The most complicated situation is in phi direction. Let's say if you have the vector here and you have a displacement in phi direction, which is shown here in this arrow, then first we need to know, let's say, the projection of r on this xy plane. So the projection of r on xy plane, let's say if it's shown here, it is r times sin theta. Then there's a small displacement here equals to the displacement here. And this is 90 degrees. Then this displacement could be written in r sin theta times d phi. Okay, so that's the ways of defining the infinitesimal displacement in three directions in the spherical coordinates: r direction, theta direction, and phi direction. And then the general infinitesimal displacement dl, here the L is a vector, it equals to the displacement in r direction plus theta direction plus phi direction. And the magnitude has been defined here or derived here. So you can see this is the displacement of dl. So this plays the role that dx times x, dy times y, dz times z unit vector played in Cartesian coordinates. So in Cartesian coordinates, you have equation of this. Similarly, in the spherical coordinates, you have an equation to describe dl in this way. So here it's x, y, z basis, and here it's r theta phi basis. And then once we have the dl, now let's talk about ds and dt, which is a surface element and volume element. But first, let's talk about the infinitesimal volume element, because that's the easy case. For the infinitesimal surface element, it's a little bit more complicated. So let's first see if we want to calculate or describe the infinitesimal volume elements dt. It equals to, of course, the LR, the L theta, the L phi. And then you put the equations of the LR, the L theta, the L phi in the same equation. Here you will get R squared sine theta, dr, d theta, d phi. It's just from those three equations. Okay, that's easy. It's easy for the volume elements. Now let's see the surface elements. For the infinitesimal surface elements, that's a little bit more complicated. Okay, let me see. There's something wrong with the picture. Let me move it back. Come back. Make it smaller so that it doesn't cover the letters. Okay, now let's see the infinitesimal surface. There's no general expression for surface elements or dA because it depends on the orientation of the surface. You simply have to analyze geometry for any given case. So here we'll try to do the um, surface element in two directions. So the first is, let's say R is constant, and then theta and phi changes, which is on the surface of a spherical object or on the sphere. So this is your dA. It's an infinitesimal small surface shown here. So of course, in this case, R doesn't change. The only thing change is theta and phi. So dA equals to d L theta times d L phi, the magnitude of L theta and magnitude of L phi. And you know, um, L theta, the L theta is shown here, the L phi is shown here. And then the direction, um, which is r hat, means the direction is going outside from the center of the sphere. Then you put all the equations for dl theta and dl phi into this equation, then you get this equation shown here. It equals to r squared sine theta, then d theta d phi times r hat. R hat is simply the direction of the um, surface element. So here you just need to remember what is the L theta, what is the L phi. They're all here. Okay, this is the one way to calculate the ds. Um, so let's see another case of ds or dA. If the surface lies in xy plane, so the theta is constant, or um, the half pi, where r and phi vary. Okay, now let's see dA2 here. Um, in this case, let's say um, the theta doesn't change because here theta is just 90 degrees or half pi. This is okay. This is a 90 degrees angle. It doesn't change no matter if the vector is moving from here to there. So the theta is always 90 degrees. The only thing changed is r. So dr changed from here to there. The r changed from here to there by dr. And then let's say a phi also changes. Phi changed from here to there by a small d phi. So dA2 equals to dLr times dL phi times theta hat. So theta hat is the direction of this dA2, or the direction of the surface. Then you plug in the dLr and dL phi, you will get finally r, dr, d phi, and then theta hat. Theta hat is the direction of your dA2. So finally, that r ranges from 0 to infinity, and phi is from 0 to 2 pi, theta is from 0 to pi. Okay, anyway, so here we just give you two examples of surfaces. or surface element. One is on the sphere or spherical object. The other one is on the xy plane. However, there might be many different uh, types of ds. It might not be on the xy plane. It could be a ds on, um, let's say, x and z plane, something like this on the xz plane. It could be some other surface which doesn't exist on any maybe plane. It's just arbitrary surface in arbitrary directions. So it's case by case. Here, in these two cases, they're relatively easy case, so you can easily express the dA by some simple equations. But for some other cases, it might be more complicated. There's no general or uniform equations for dA. This is a different thing than dt, because for dt you have a general equation. It's always dt equals d lr times d l theta times d l phi. Okay, now let's see one example. Find the volume of the sphere of a radius capital R. Okay, so that's a simple test. It's easy, which is integral of, which is the volume integral. So it's integral of dt. So it's a three-dimensional integral of dt, and dt could be written in this way: r squared sine theta times dr d theta d phi. So let's use r squared sine theta dr d theta d phi. And r should be from 0 to capital R because the radius is r. Theta is from 0 to pi, phi is from 0 to 2 pi, as we described the range of theta and phi in this figure. So the range is simply pi, 0 to pi for theta, and 0 to 2 pi for phi. Because this is three-dimensional integral, so you can read it into three individual integrals, and the product of those three integrals will be your final answer. Let's see, for the first term, let me change to another color to make it easier to read. Of course, it equals to from integral from 0 to r d, let's say 1/3 of r cubic. If you are familiar with integral, so this could be, so this term could be written into this term. So finally, you need to calculate 1/3 of r cubic from 0 to r. You just plug in 0 and r into the equation. You will get the integral of the first term. For the second term, it's 0 to pi d negative cosine theta. Do you remember this derivative? D cosine theta equals to negative sine theta. So d negative cosine theta equals to sine theta, d theta. Then you just need to calculate negative cosine theta from 0 to pi. That's the second term. For the third term, it's easiest. You just need to calculate the phi from 0 to pi, and the value of The third term is, of course, 2 pi. And then you do the product or multiplication of those three terms. Finally, you will get the answer, which is um, 4 pi r cubic over 3. So this is the volume equation for sphere. And it could be calculated by this volume integral, the basic volume integral from the spherical coordinates. Now, let's see. Okay. Let's see the translate vector derivatives, which is gradient, divergence, curl, and Laplacian. So we know that del t equals to dt dx times x direction plus dt dy in y direction plus dt dz times z direction, which is the unit vector of the x z axis. And then this is in the Cartesian coordinates. If we want to express del t in spherical coordinates, what we can do is we can write it in the chain rule to expand the partials. So partial t partial x equals to partial t partial r times partial r partial x, and then partial t partial theta times partial theta partial x, partial t partial phi, then partial phi partial x. And we know x equals to r theta cosine phi. Then let's say partial r partial x. How to write partial r partial x? You can use this equation to express the relationship or the partial derivative. And similarly for the other terms, you can also get the derivatives. And then here we don't derive it from the scratch. It will cost a long time. So what we were giving here is the final equations for the gradient, divergence, curl, Laplacian. So for gradient, del t equals to partial t partial r in r direction plus 1 over r partial t partial theta in theta direction plus 1 over r sine theta partial t partial phi in phi direction. And here is a divergence equation, and here is a curl for a vector function, and here's a Laplacian equation. So all of these are for functions in r theta phi coordinates or in the spherical coordinates. It seems like much more complicated than xyz coordinates. However, sometimes it's more useful. It's difficult to remember all of those equations, so for reference, those formulas are listed in the front cover, so it's in the textbook. You can put this in the cheat sheet in the exam, so you don't have to really remember all of these. Okay, so that's for spherical coordinates. Now let's look at the cylindrical coordinates. In cylindrical coordinates, let's see, it's shown here. In cylindrical coordinates, we have a z direction. We also have an s, which is here, and then the phi. which is the angle shown here. So by defining S, phi, and Z, you can always get any position in the three-dimensional space. Of course, this position can also be described by XYZ coordinates, and here sometimes it's easier or more convenient to be described by cylindrical coordinates S, phi, Z. Okay, so if this is S, this is phi, this is Z, so the relationship between S, phi, Z and XYZ could be written here. So first, what is X? So in this example, X is shown here. So this is in the red line, it's S, means here it's S, and here it's 90 degrees. So X equals to S times cosine theta, because this is 90 degrees. The same similar thing in Y equals to, because here it's Y. So sorry, not here, but here it's Y. So this is the Y direction. So Y equals to S sine theta, sine phi. And then Z, which is shown here, it's the same Z in Cartesian coordinates. And the unit vector can be shown as S phi Z hat equals to cosine phi X plus sine phi times Y direction. And phi, the unit vector of phi equals to negative sine phi in x direction plus cosine phi in x direction, and z equals to z direction, which is going up. So these can be calculated easily by trigonometry. If you look into the figure, you can easily derive those equations. The infinitesimal displacement are first dls. Okay, so dls equals to ds because it's just in the x direction. dl phi, which is s d phi, because this is s. Let me write it again. So this is s, so this is also s. If you have s here, s d phi equals to, let's see, what happens with my, okay, so now let's see, let's make a picture here. Let's say this is in the d phi direction, which is going this way. Then the L phi, let's say it's the L phi. The L phi in phi direction. It equals to, first this is s times, this is d phi. So s times d phi equals to the displacement in d phi direction, which is s times d phi, which is very similar to this case. D theta equals to r, dl theta equals to r times d theta. So now here, the L phi equals to S times d phi. And dz, the Lz, of course, equals to dz. It's just going up. And the volume element is dt equals to all to the product of these three terms, which is s, ds, d phi, dz. And the range of s is from 0 to infinity. Phi is from 0 to 2 pi. Z is from negative infinity to positive infinity. And then the vector derivatives in cylindrical coordinates could be written similarly in those four equations: gradient, divergence, curl, and Laplacian. The formulas are also listed in the front cover, so you don't have to remember those equations. You can always go to the textbook to refer to those equations. Okay, so that's all the knowledge you have to know for cylindrical and spherical coordinates. So that's our lecture 6. I'll see you in next lecture. Thank you.